Okay, good. Okay, so well, today it is my pleasure to introduce Assa. Actually, well, Assa doesn't really need an introduction in this forum. So, so literally, the mic is yours, Assa.
Okay, thank you. So let me share the screen. Okay. So this is a talk which covers different kinds of projects that I've been involved in. But the reason I think it has more general interest to physicists outside condensed matter is the subject matter is actually quite general in understanding currents. So we know that metals can transport currents, but then the question is what exactly is moving in the metal is actually an open question sometimes. And it's actually a very intriguing question because it tells you not only information about band structure, but also about interactions and about correlations that are non-trivial. And you can find out those correlations or find out something about those correlations through the Hall effect. So this is a topic about how you use the Hall effect to understand currents in general. And the reason I was involved in this question is that I was faced with certain anomalies that appear in superconductors and also in metals that are called bad metals or metals with strong electron-electron interaction like the cuprates. And those anomalies are difficult to understand within the classical and the simple-minded theories of metals, and that's why they're called anomalies. For instance, in superconductors, it was seen quite commonly that the Hall effect changes sign. And in cuprate superconductors, next to the Mott insulator, there was a divergence seen, and the divergence is not expected by any simple theory of metals. So these were the two phenomena that motivated this talk. But the talk is more general than that. And the subject of what really moves in a current has bothered the greatest physicists of the 20th century. We see Landau and Drude, who wrote the theory of transport in metals, and then, or transport in gases, and then in metals, and then, of course, Boltzmann and Maxwell, who were very interested in thermodynamics and statistical mechanics of gases. And we essentially phrase some of the problems that we're going to see in terms of dilemmas that bothered them as well. So magnetic field can tell you if a charged particle has a plus charge or a minus charge. We know that from bubble chambers. You shoot a charged particle, and if it turns right, it's a positive particle, and if it turns left, it's a negative particle. So the similar effect, which comes from the Lorentz force of a magnetic field on a moving charge, affects currents in metals. And here I ran across some history that maybe some of you know. I know that Yossi Avron knows this history very well. Edwin Hall, who discovered the Hall effect, wrote this beautiful paper, which I like the introduction very much. So I'll read it to you. Sometime during the last university year, while I was reading Maxwell's Electricity and Magnetism in connection with Professor Rowland's lectures, my attention was particularly attracted by the following passage, and this is a quote from Maxwell. It must be carefully remembered that the mechanical force which urges a conductor carrying a current across the lines of a magnetic force acts not on the electric current, but on the conductor which carries it. This sounds a bit curious because we know that magnetic force acts on charged particles and the current is carried by electrons, but I guess Maxwell at the time was not convinced that the current was carried by particles. So he predicted that the force will act only on the metal, on the solid. However, of course, the Hall effect shows the opposite. It shows, and this is what Hall wrote in his paper, the phenomena observed was just such as we should expect to see if the electric current were pressed, not moved toward one side of the conductor. In other words, the force really is acting on the current, which produces a transverse voltage or a transverse pressure, if you want. And that essentially showed that Maxwell was wrong about this, and started the whole business of the Hall effect. So the Hall effect is an effect which we explain early on to students in a very simple-minded way, which is wrong actually for real materials, but it's easy to explain to students based on the Lorentz force. The idea is that if we have essentially a voltage acting on charged particles in a magnetic field, they will produce this kind of a cyclotron motion, and they will be moving at some velocity, and one can compute the velocity very simply if we assume translational symmetry and no longitudinal conductivity or resistivity. So how do we compute the velocity? Well, we go to the moving frame. In a moving frame with velocity v, we can tune the velocity such that the electric field vanishes. And that will give us a velocity which is E cross B divided by B squared times C, which is the Lorentz transformation needed to nullify the electric field. And then we get particles that just move in circles and not move anywhere, so the current is zero in the moving frame. Going back to the laboratory frame and plugging in this value of V, we of course get that the relation between the electric field and the current is given by N, charge of the particles, C divided by B. So all this exercise is to show that the Hall effect in the end tells us something about the charge density, N times Q, in the metal. And if you have electrons, you expect Q to be minus the magnitude of the electron charge. And this is a well-known formula, which of course is not correct in a metal which has impurities and disorder. And one needs to go to a bit more sophisticated theory to do that. Anyways, the theory of metals written by Drude allows you to write the Hall effect in taking into consideration disorder and scattering. So in the limit of weak scattering, which is important, you still have a free electron gas. It's being diffusing around, scattering off impurities. If you put an electric field, those electrons start drifting at some velocity and will give you a current in the direction of J. The current doesn't have to be parallel to E or perpendicular, it can be in any angle. So there'll be two conductivities, the longitudinal conductivity sigma xx in this case, and sigma xy, which is the Hall conductivity. In Drude theory, the values of those conductivities are given in terms of the scattering lifetimes. And this is the tensor, the sigma xx on the diagonal, assuming here a C4 symmetry, and the Hall effect is the off-diagonal antisymmetric part of the conductivity. The longitudinal conductivity in Drude formula is the density times electric charge squared times the lifetime divided by the mass, effective mass, if you're a more complicated theory. And the Hall effect is given by even a more complicated formula that depends on the scattering lifetime squared. And it is definitely different than the Galilean invariant result we showed in the last transparency, especially because it depends on the scattering lifetime, and it doesn't go like 1 over B, but it goes linearly with B, as you can see in this formula. So you can see that life becomes complicated. However, in a miraculous way, the inverse of the conductivity, which is the resistivity tensor, gives you a quantity called Hall coefficient, which is essentially the derivative of the Hall of the rho xy or rho yx divided over B at weak fields at B equals 0. And if you plug in those expressions and take B to be small, you get this expression. And if you plug in these two expressions into here, a miracle happens, and the scattering lifetime, which appears here to the second power and twice appears here. The first pass cancels out, but not only the scattering time, also the mass cancels out. And you get a number which is just 1 over the density times E and C, which are fundamental constants. So somehow the Hall coefficient just measures, in Drude theory, the inverse density. And this elimination of scattering lifetimes and so on has been very useful, because the Hall coefficient has been used to characterize semiconductors, metals, and many, many different systems, just based on this simple formula. So the question one can ask is, does this formula hold always? And obviously not. And we'll see when it starts deviating from this formula. But there is something that we'll show later on survives even much more complicated Hamiltonians or much more complicated systems. And that is that the Hall coefficient, as you can see, does not depend on any dynamics. It doesn't have things like lifetimes and masses which enter, time-dependent phenomena. It just measures density, which in a sense is like a thermodynamic quantity that you get from derivatives of the free energy. And this actually is a property that I have shown in my formulas is generalizable. So the question will be answered later on in this talk. But I take a side tour into some history, because someone pointed out when I gave this talk in Paris last year that the question of holes and having a positively charged Hall effect was actually very important in the development of the condensed matter theory, condensed matter physics. There's a very beautiful review of modern physics written by Hotzenbein and Eckert, Quantum Theory of Metals, I recommend reading. And it tells the nice story about holes. So we know that when you have a band and you fill it more than half filling, you can start describing the band with holes. But that wasn't clear at the time. But the Hall effect was measured to give both a negative sign and a positive sign in different metals. And Heisenberg had a very smart student, Peierls, who, as you know, also beat him to understanding the critical mass of a nuclear chain reaction. But this was actually more interesting. The question he gave him here, which was his thesis question, was more interesting to this talk. He wanted him to account for the variation in Hall voltage with temperature and magnetic field and explain why for certain metals again the wrong magnitude and sometimes even the wrong sign. And Peierls wrote down a theory where he showed that when you have a band structure, he was basing his theory on Bloch's theorem and band theorem for electrons in solids. And when you fill up the band enough, you can start describing the current not by the electrons that are filled, but the states that are not filled, and they call them holes. And they act in the Hall effect with the opposite sign to the electron sign. And this theory, written in 1929, preceded Dirac's very innovative idea of understanding or predicting essentially the existence of positrons as holes in the Dirac sea. Now, what's written in this paper, is this history paper, is that Bethe noticed that Dirac did not refer to Peierls in his theory of the Dirac sea. And the reason probably was that the omission in part of the relation between the theories, partly due to the fact that Dirac holes were not generally taken seriously until after the positron was discovered in 1932. So as you can see, these are very deep questions of what really is governing the currents of elementary particles and of course, solid state particles. So let me explain holes in a very simplistic way. So imagine you have a band and you fill up all the electrons up to the Fermi level. This band generally will have zero current because you filled up same amount of positive K and negative K, and time reversal tells you that you have the same amount of states in both directions, and therefore the system will not carry a current. However, if you take and you add one extra electron, now this electron does not have one to cancel it, so it has a velocity which is the slope of the dispersion, and overall there'll be a current E times V. And what Piles pointed out is you can also think about the same current as carried by this one extra hole in the sea of holes that are filled symmetrically on both sides of the band. And therefore, you have a current which is carried by the hole. It has the opposite velocity, so it has a velocity v hole which is negative to VE, and it has the opposite charge. So in a sense, you can either describe the current as carrying by holes or by electrons. In this particular simple picture, you cannot tell the difference because there's a particle-hole symmetry. However, in general, there is a way to tell whether it's the electrons or the holes that actually carry the current. So this dichotomy is lifted by the Hall effect. And the Hall effect can actually tell you what really is moving here, the particles or the holes. So this is an illustration of what I mean by not knowing what is moving. In this case, are the white birds flying, or the black birds, which are the shadows of the white birds, are flying, and so on. But analogy is very loose. Okay. So now that we have holes and we have electrons and you have band structures, as we know, are given by these dispersions in the Brillouin zone. And when you cut it with a Fermi level, then you form Fermi surfaces of all the states at the Fermi energy, and they form some kind of a two-dimensional surface. It could be a sphere or something more complicated. And the current is carried by excitations, like we saw before, of particles excited above the Fermi level and holes below the Fermi level. And those particles will carry the current and will give you all the transport you need. At low temperatures, you're really discussing only the K states very close to the Fermi level. However, all this theory that was written here, these beautiful pictures, are only valid if the scattering is much larger than the wave vector of the Fermi level. So here, if your wave vector is kf, then your wavelength is 2 pi over kf. The wavelength has to be shorter than the distance between scatterers. Otherwise, you cannot really define well-defined K states and the Fermi surface is destroyed. So if the band theory is valid, which it is in many good metals, one could use a more complicated transport theory than drew there, which is called Fermi liquid Boltzmann theory. And in Boltzmann theory, the Hall coefficient also acquires a very simple description without referring to dynamics or complicated scattering processes. The Hall sign weak scattering is really given by the curvature of the Fermi surface. So an example is just a two-dimensional band structure, which is given by circles close to the K equals 0 and circles around the pi points. The low energy states called electrons, they have essentially parabolic type of energy dispersions would look like free electrons. Here you have the holes, which is parabolic with the opposite sign of the parabola. And again, you can describe this as free holes. So the Hall effect, both very close to the bottom of the band and top of the band, is diverging like 1 over n, as we showed the Drude formula giving us. And here it diverges like 1 over 2 minus n. Here it has a negative sign, a positive sign. And when the when the density actually is exactly at half filling, you fill the full diamond, the Hall effect vanishes. So it's quite a simple picture, and it's quite general. One can distort the Fermi level a bit, and you still get these two divergences in the band bottom and maximum, but everywhere in the middle of the band, the Hall coefficient is finite. It could cross 0 at different points, but it's not ever having any divergences or anything like that. So this is an important thing to remember from Fermi liquid and Boltzmann theory. In case we do find any divergences in the middle of the band, we know that we ran into some problem with that theory. And I'm already giving you a spoiler that this theory fails quite miserably for a system with strong electron-electron interactions. So I'm now going to discuss, before we go further into strong interacting metals, I'm going to discuss a very interesting Hall anomaly seen in superconductors. What I mean by Hall anomaly here is that unlike what we saw before, that the Hall sign and the Hall magnitude is dependent on the Hall density and perhaps on the Fermi surface shape, experiments in superconductors, in the metallic regime of superconductors, in other words, in the regime where the superconductors start to conduct when you put strong enough field on them and strong enough voltages and so on. And in those regimes, a sign reversal has been sometimes observed. Sign reversal of the Hall coefficient as a function of either temperature or magnetic field. And definitely these are Hall anomalies, because what can make suddenly carriers of certain sign change their sign as a function of temperature? This has been a very old and important problem that has been in the literature for a long time. So I would estimate even more than 50 years of controversies about what is causing the Hall effect to change sign in these superconductors. And this is just a random assortment of papers by very distinguished groups. Most famous here is the Nozier and Vinin, which is the oldest, and then there's a lot of groups from ETH, from Russia, from different parts of the world, and they all are discussing the cause of the Hall coefficient suddenly changing sign unexpectedly in this regime of close to superconductivity. So before I can explain to you what we have concluded about this effect, let me give a short review on superconductivity on the context of what is important for the transport. So superconductivity is essentially a phase of a metal which responds to an external field, or an external Aharonov-Bohm field in this case, in a very specific way. If you approach a superconductor with a magnet, you will cause an EMF to make a current flow around. But then when you stop moving the magnet, in a regular metal, the current will decay, but in a superconductor, the current will persist. And the persistent current induced by a static Aharonov-Bohm flux is a hallmark of superconductivity. It cannot happen if the resistance was different than absolute zero. By the way, Mitkeren is using this effect to measure important properties of superconductors by passing essentially a very long coil, which imitates the Aharonov-Bohm effect in the whole of the superconductor. What is important about superconductivity that we need to remember is the concept of wave function rigidity. Wave function rigidity, a concept developed by Anderson, is really the fact that a superconductor is defined by some very interesting degree of freedom called phase, which could change as a function of position. It describes the order parameter of the superconductor, and it can wind around the circle. And the free energy depends on the gradient of the phase and the gauge field that it's exposed to squared. So it's like an elastic theory. It means that the free energy will be minimized if the phase is constant, but it could allow for the phase not to be constant. If it's not constant, it means that there is a persistent current flowing. So the persistent current is actually a twist stress, exactly like in elasticity. When you describe a stress, you describe essentially a derivative of the energy with respect to strain. The same happens in a superconductor, but now the stress is actually a persistent current. Now, a rigid body can survive a stress, right? Unless you put it too much stress and you break it. Surviving the stress is what the superconductor knows how to do. And this is a measure of this stress. If you twist a coil and you ask what is the energy doing as a function of the twist, it's exactly like the free energy of a superconductor. And the rigidity of the coil, or how difficult it is, or what the size of the energy is as a function of twist, is this rho s, which is the coefficient of the persistent current. It's what's called the superfluid stiffness, or bad notation, superfluid density, but it's really a stiffness. Okay, so this is really the hallmark of superconductivity, and without it, there will be no superconductivity. Okay, and the second thing to remember about superconductors, if you expose them to a penetrating magnetic field, so now the superconductor is on the blue film here, it's a narrow film, so it's not going to produce much magnetization. You put a magnetic field on it, vortices will form. Vortices will just alleviate some of the stress introduced by the penetrating magnetic field and form circulating currents around certain points. Now, it's not just generally certain points that will give you vortices, not any points, because the interaction energy between two vortices is very strong and long range. It goes logarithmically. It's like charged particles in 2 dimensions. This means that the vortex lattice that is formed here due to the magnetic field will have a well-defined lattice constant or distance between them. So since the vortices repel logarithmically, the vortex lattice is incompressible at the density, which is fixed by the field, and this is the equation. If you give me the field at a certain point, I will tell you what is, to very high precision, the vortex density in that regime. It's essentially a form of charge flux attachment, if you want. There's a magnetic field and a vortex position, which are, or vortex density, which are highly related, and talk about it later. So this is what we need to know. And now we go into vortex motion. So Josephson, who was Anderson's student in Cambridge at the time, came out with a very remarkable relation between the motion of vortices. So vortices could move, but if they move, they will produce a transverse electromotive force, or if it was in a superfluid, it would be a pressure drop. And this is the explanation using the phases of the order parameter and how they rotate when a vortex moves. So rotate is a winding of the phase around the position of the vortex. But the motion will produce an EMF, essentially a chemical potential drop, which is given by the velocity of the phase, the gradient of the velocity of the phase. So this relation, due to Josephson, is extremely important, because if vortices move, you will have finite voltages on your system, or finite EMF. So now we're into flux flow. So flux flow is a regime of superconductors in the temperature magnetic field phase diagram, where if you look at low fields and low temperature, I describe the vortex lattice. But if you increase temperature and increase magnetic field, and remember, these are thin films, you could have a regime where the vortices can move quite easily if you put any kind of field on them that would want to make them move. Once the vortices move, voltages will develop and the system will behave like a metal. But it's not a real metal, because the real metal is something you're going to see above TC at zero field, and that behaves according to the theory of metals we described before, or some other theory, but it's quite different than this regime, because this regime is essentially a superconductor with a vortex lattice that is crawling along in some direction. So it still has the superconducting rigidity, at least as far as the interaction between the vortices go. So again, you have a magnetic field, you have a vortex lattice. This is the size of the core of the vortex lattice. This is the average distance between the vortices. Everything is dictated by the magnetic field. And now you connect a voltage to it. So immediately I can hear through the Zoom, just because I hear from the corridor the yelling of the experimentalists saying, what do you mean you're connecting a voltage to a superconductor? You're going to get a short. And the short, of course, will make the lab explode, and you know, all the other difficult consequences of that. So is that really what's going to happen when you put a voltage in a superconductor? The answer is mostly yes, unless you're in this flux flow phase. If you're in the flux flow phase, then instead of allowing an infinite current to increase linearly in time, the vortices will start moving. Once they move, they will produce this Josephson EMF, which will be exactly equal to the electric field that you introduced with the battery. And now everything is finite. The vortices move at some velocity. The velocity is determined by the electric field and the magnetic field, and it's a steady state. Nothing is really changing in time. I mean, there's noise and stuff, but nothing DC is changing. And it is really the only possible flux flow steady state that you can have, one which the current doesn't increase linearly in time, is the one where the vortices on the average move exactly with this E cross B divided by B squared velocity. So the reason I'm posting this picture of the flux flow, which is quite different than the one you see in the 10 to the 4 paper we saw before, is that I'm looking at the response to an electric field rather than to a current. And by that, I'm avoiding all the difficulties that people have run into trying to write down equations of motions for vortices to predict what is going to be their velocity as a function of current, let's say. Here, the velocity is completely dictated. There are no parameters that are related to the material properties of the superconductor. It's a pure relation, nearly a tautology, that the velocity of the vortices is precisely dictated by B and E alone. And of course, the velocity of light. Okay, so now we have a system where vortices are moving, but there's still currents in the system. There's a longitudinal current that's going to flow through the red circle and a Hall current to the blue. And the problem of flux flow transport is to predict what are these currents. And as we said, we found that the Hall current had some funny behavior and sign changes that we want to understand. Bardeen and Stephen gave a theory for the flux flow, and they showed that if you start at high fields and reduce the field, keeping the temperature fixed, you get a very simple behavior according to their theory. The longitudinal resistance will just be the normal phase resistance at high fields, and then below BC2, which is the nominal critical field where the system is supposed to turn from metal to superconductor.
כן, אבל כנראה שבפנים כל אוניברסיטה עושה את השכלולים ואת ההתאמות שלה. כי גם אני לא מסתדרת אפילו עם המודל של אוניברסיטת חיפה. תאמין לי, אני אחת שיודעת לעבוד עם מודל.
לא כך הבנתי. מה אתה חושבת שהמודל של האוניברסיטה...
Sorry, yes, unmute yourself. I muted everybody, but unmute yourself.
Yeah, okay. So Bardeen and Stephen gave a very simple prediction. They said, in this flux flow regime, just take the normal state resistivity multiplied by B divided by BC2. BC2 is this red curve that is where the system wants to turn normal, whatever that means. It's a mean field type of energy field scale that you get from the Ginzburg-Landau theory. Doesn't matter here. It just says that there's going to be a reduction in the resistivity in the flux flow regime, and also a reduction in the Hall resistivity, which will have the same factor, and it'll go quadratically in the flux flow regime. However, Bardeen and Stephen predicted the Hall sign is going to be exactly the same as the Hall sign in the normal phase. There's not going to be any change of sign of carriers. That's why when people observed this anomaly, which is suddenly a reversal of the Hall sign, it was considered a very mysterious thing that showed the breakdown of Bardeen-Stephen theory. And the question, of course, how to fix Bardeen-Stephen theory was the subject of all these controversies. So in the paper last year with Danarovas, we gave our position on this matter, and we built up the theory of transport, as I showed before, from the response of the vortices to an electric field, not to a current. When a vortex moves, okay, this is essentially the current that goes around the vortex. When the vortex moves with velocity v, the phase twisting, as we said, produces an EMF field that looks like a dipole configuration around the vortex core. Inside the vortex core, there is a linear electromotive force that is dependent on this velocity as well, and also on the radius of the vortex core. Now, if you take a bunch of vortices in a vortex lattice and let them all move each one of them will produce like a dipolar EMF configuration, which adds up precisely to the electric field that you imposed on the system to give you the steady state condition, the Josephson steady state condition. Now, there are two contributions to the current. First of all, the cores themselves are metallic inclusions. So we believe they behave similar to the normal state transport coefficients, especially when the temperature is not far from TC. So it's essentially just an extension of the normal state into the regime where the order parameter vanishes because of the high currents in the vortex core. And then we know how the current voltage behavior is given there. It's given by sigma core, which is not very different than the normal state conductivity. Now that relation of E core to sigma core is giving me J of core will give me a current density which is the same, more or less, in all these different vortices that are moving in the same velocity. And they all add up. They all add up. The effect of the medium, which is superconductor, is simply to allow the currents to keep up completely undisturbed and unscattered in the superconducting medium between the vortex cores. And this is due to the fact that the superconductor only allows laminar flow, potential flow. So it cannot allow the current to do circles and turn around and come back. Once you know what the currents are everywhere, then you just add them up and you get the contribution of the full current due to the motion of the cores, and that's this first term. So the first term is going to be E times sigma is J, but E is E core B over BC2, and when you invert it to write the current as a function of E external, you would see that it has a factor of BC2 over B, and this is precisely, the first term marked here, is precisely the result of Bardeen and Stephen, both for sigma xx and sigma xy. So notice the relation is written here for conductivities, but it's the same relation as Bardeen and Stephen found for resistivities. However, there's another term. The other term is related to the fact that the vortices themselves may carry charge, and we'll see later why that can happen. If the vortex attracts some electric charge with it, it moves precisely, as Josephson says, perpendicular to the electric field, and therefore its motion could carry a current, which will be a Hall current. So there'll be a Hall contribution, which is very simple. It's written in terms of 2E Q over H. If you remember, this is very similar to the formulas you get in the quantum Hall effect of E squared over H times some effective charge of the quasi-particles. So this is the flux flow analog. Now the question is, what is the value of this QV? We'll discuss it soon. But if you assume there is some charge attached to the vortex, obviously it can only contribute to the Hall current because the vortices move perpendicular to E. Now the question is, what is the size of QV? And this is a source of argument in the literature. The vortices are moving, fine, but how much charge are they dragging with them? Well, there's two charges one could describe. One is the depletion of the charge, or maybe extra charge, attached to the vortex position. Let's call it QV. And the other one is the condensate density. Now, when the vortices are moving, when the flux flow is happening, one can describe it as if the Hamiltonian is moving at velocity v. It's just a way of writing the electric field in terms of a time-dependent gauge field. So the Hamiltonian is moving slowly to the right at velocity v. I say slowly because everything has to be adiabatically. And immediately, some people, maybe even in the audience, would say, let's invoke the adiabatic theorem. Adiabatic theorem tells you if a Hamiltonian is moving slowly at some velocity, all the wave functions and all the matter and everything that is attached to the Hamiltonian will move at that velocity, and you'll have a current which goes like the number of Cooper pairs in this case times the density times the velocity. This is what you get from adiabatic symmetry arguments or adiabatic theorem arguments. Galilean symmetry will give you similar results. You say, oh, I have a moving condensate, I have a moving system, let's go to the moving frame, and then everything is at rest there, and then you go back to the stationary frame, you say the current has to be 2E and V. However, it's wrong. And the reason it's wrong is actually very deep. It's because we're discussing a superconductor and not a normal metal or not a system of independent particles. A superconductor has a broken gauge symmetry, if you want, or it has rigidity, as we described it before, of the phase. And this rigidity would prevent the condensate from moving. It also will tell you that these charges are completely rigid. In other words, the vortex distance between them is rigid. It's incompressible. You know, there's no way that these vortices can collide and come close to each other and so on and mess up what we mean by a vortex charge. So there are two properties of the superconductor, the vortex lattice incompressibility and the superfluid condensate cannot be dragged, which gives us that the only thing moving here will be whatever is attached to the vortex position, which is the vortex charge. And this is a picture of what's going on. So you see that the density is actually staying the same, but what is moving is the vortex charge. Now, the moving vortex charge is something I have to define a bit better soon, but it's a quantity that is attached to the vortex position. And once you accept that, then the whole current is going to be that charge times the density of vortices, which is proportional to the magnetic field, times the velocity, which given by a Josephson relation. So let me give you a very kind of hand-waving discussion of why you don't drag the superconductor when you move the Hamiltonian. It's like you cannot really row in a superconducting lake. So this is an example of rowing in a classical lake, in a regular hydrodynamics, and you impart momentum into the condensate, in this case the lake, and that gives you the momentum to move the boats. However, in a superfluid lake, this other team is trying to row, but their oar, as long as they're not pulling it too fast, is just moving, and the laminar potential flow here cannot really accept any momentum or any force from which is momentum over time from the rowers. So these rowers are not moving anywhere. So it's the same point that I wanted to show before, that when you move the Hamiltonian, in this case the oars, you're not dragging or you're not imparting momentum to the condensate. So now we want to ask how to calculate this vortex charge. And there's a Ginzburg-Landau theory. I won't go too much into the formulas here. There's a local chemical potential, which is proportional to the kinetic energy due to the strong currents around the vortices. That local chemical potential is related to the electrical potential because of screening. And you can, as you can do in all other Coulomb charge systems, extract the charge associated with the deviation of the chemical potential by Poisson's equation, and you get that it's oppositely in sign to the chemical potential. And when you take this equation and you integrate it over the cell, you get the total charge that is associated with the vortex position. And the total charge is given by a very simple formula that I can explain. It has some magnitude, and it has a logarithmic in magnetic field divided by BC2. BC2 is related to psi, the vortex core size. So, and B is related to the distance between vortices. So essentially you have to integrate 1 over r squared over 2 dimensions of a distance, which is related to B, and the integral will give you a log of 1 over B. So the magnitude of Q0 is actually an important quantity. Ask how many electrons are dragged by the vortices. It's related to how much the superfluid stiffness depends on density. The derivative of the superfluid stiffness with respect to density will determine this coefficient, and then there's some other material dependent coefficient like screening and lattice constant and so on. But overall, the most important thing to remember, it has 2 features. First of all, it's opposite in sign in general to the normal state carrier. This will explain the whole anomaly. It gives you a correction which is negative to the conductivity, and it could cross 0 if it's large enough, which it usually is at weak magnetic field when this becomes large. And it's of order between 0.1 to 1 electron per vortex per layer. So this is the prediction of this theory, and there are data that we managed to fit to that theory. This data of the Kim's group in Harvard from 2 years ago, and data that has not been published yet, hopefully soon, by Amit Kanigel and Yuval Nitzav, that shows this Hall anomaly. And from the Hall anomaly of Rxx and Rxy, one can extract the vortex charge. And the reason for the sign inversion is due to that charge. And this is a fit to the log B, and the magnitude of the vortex charge is given here by fitting essentially the dielectric constant, which we don't know very accurately, but the dielectric constant looks reasonable, between close to 10 in these materials. So what I want to just say is that this is a theory that has not yet been tested well enough against enough experiments. And hopefully scanning or capacitance would detect this vortex charge directly and also see the sign. Because a large part of the controversies that you've seen before were about the sign of the vortex charge, if it's involved in the Hall effect. And we have a prediction that should be tested. Okay, so let me see how we're doing in time. Okay, good. So I'm just now going to talk about the other Hall anomaly, which is the Hall anomaly due to strong electron-electron interactions. This is a material which happens to be a high-temperature superconductors, but here I'm not interested in the superconductivity, but in its normal state, normal, I say quote-unquote, normal state behavior of the Hall coefficient as you go towards half filling, and notice that it looks like it diverges like 1 over the distance from half filling, in blatant contradiction to the prediction of band theory or Fermi liquid theory. Fermi liquid theory, even if you tweak it enough to give you the positive sign, because you need to do some changes of the band structure to make the band structure Hall-like in this regime, still it will never diverge as you approach this limit. Now, in this limit, the system turns insulating because of strong electron-electron interactions. So one can suspect that these properties of strong electron interactions, which are not taken care of correctly in the perturbative Fermi liquid approaches, would also affect the Hall effect. So this is the anomaly. And the question is, how can you explain it? And the answer is one has to calculate the Hall coefficient for a model that describes these materials. And these models are well known and have been studied, but the Hall coefficient has never been calculated yet. In these materials, this is a different cuprates, but it's the same in the cuprate we showed before. The longitudinal resistivity is very, very high. And it exceeds the limit where the scattering length becomes even shorter than the wavelength of the electrons. So by exceeding this limit, which is called Joffe-Regel bound, we know that one cannot use Boltzmann theory to understand the currents or the transport in any way. If you want to push transport theory to strong interactions, you're facing serious problems when it comes to conductivities. The Boltzmann equation is invalid. If you want to do multi-band models, they're very, very cumbersome. Numerical calculations of conductivities are very limited by size effects and analytic continuation problems and so on. However, we have developed, and I'm saying it's people I worked with for a while, like my previous students, Netanel and Ilya and Omer and others, we all worked on this development of an alternative approach to calculating conductivities using hyperspace. And of course, Colloquium is not a place to teach hyperspace, but just to say that there's interesting mathematics of treating the response functions not through wave functions, but through operators and their commutations. Mostly the commutation with the Hamiltonian, which is the Liouvillean, and the inversion of the Liouvillean, both real and imaginary parts, are important to derive the conductivities. So the Kubo formula, which is the formula for conductivities, is now given in terms of these formal matrix elements between current, which are now like states, and the inverse Liouvillean. So it's a very compact notation, and one can say, what is the usefulness of this notation? The usefulness is that it allows a starting point for deriving new approaches for calculating both sigma xx and sigma whole. For instance, for sigma xx, this is the starting point for continued fraction expansion, which, as you can see, these authors have worked on. And the Hall effect is what I have derived for the weak field limit of the Hall conductivity in an expansion in field. So in other words, take the derivative of this expression with the field. Now, of course, all these quantities depend on the magnetic field, including the inner product and the density matrix and so on. And eventually I got this expression that is, again, totally formal, but it's the first advantage of this approach is it's amenable to changing the Hamiltonian to a simpler Hamiltonian. So when you use the bottom expression, you could use a low energy effective Hamiltonian to calculate the Hall coefficient. And what I found was that this expression can be written as a product of the longitudinal conductivity squared times a quantity that is independent of scattering dynamics and of any dissipative process that enters the conductivities. They all drop out because RH, the Hall conductivity, is sigma to the -2 dHdB. So if you multiply this by sigma to the -2, sigma, which depends on dissipation and on scattering lifetime, drops out, and you're left with an expression which generalizes this Drude result that you can express the Hall coefficient in terms of quantities that are totally evaluated in static thermodynamics approaches. So the Hall coefficient is given by this formula, and these papers that show it, and there's a recent application with my postdoc Abhishek Samanta, which applied it for semi-metals and interesting band structures. But without going into explaining what the formulas are, I just say that the advantages that they're all static thermodynamic coefficients, they're computable by high temperature series, Monte Carlo, and other methods that have been developed for statistical mechanics. And mostly important, we don't need analytic continuation, which is the problem of getting conductivities, especially DC conductivities by quantum Monte Carlo. I should add that there are two other formulas which have not been yet exploited, the Nernst and the thermal Hall coefficient, which are very similar to these coefficients, to these formulas. Now in cuprates, the model is quite different than the simple band structure that we showed before for metals. We have spins strongly interacting, holes moving around. This is the simple picture of a cuprate conducting layer. And therefore, when you put one electron per site, you actually form an insulator where each spin is occupied singly at every site, and there's a gap, quite a large gap, formed by the strong electron-electron interaction, and this is a Mott insulator. So the Mott insulator is definitely not something you get within band theory. And also, when you go not far away from there, and by doping into holes, by plucking a few spins out, you end up with a high temperature superconductor. So this is a fascinating phase diagram that very little is yet being agreed on and understood on why it happens. But I'm not asking why the system turns into a superconductor. I just want to calculate the Hall effect for the simplest model of these spins and holes. And the simplest model is called the TJ model. It's actually drawn on the cover of my textbook. It describes spins, holes, and the spins can hop around, and they can interact with each other, but their hopping is highly restricted. That's what's important. They're not free hopping like electrons in a metal. They depend on a constraint. They cannot doubly occupy any site. So therefore, there are no Bloch wave-like eigenstates, Fermi liquid eigenstates, to describe the system. And one could use my formula, which is what Ilya and I did, for high temperature. At high temperature, the calculation simplifies a lot. It just becomes traces of commutators of operators, and we got this result. This is the result of the Hall coefficient as a function of density of electrons, plus another correction I won't get into, and as a finite temperature. And it's a result that completely changes the picture from the band theory that people have been using. So the band theory is the blue curve. That's the one we saw before. It should not diverge at half filling. It's actually 0 at half filling, and it diverges only at n equal 1 and 2, 0 and 2. But this expression is totally different. First of all, it changes sign. You can see, even when you're below half filling, you become hole-like. And then it crosses, changes sign again, diverges, and then it comes back, changes sign, and becomes like free hole. So everywhere around half filling, the physics of the Mott-ness, strongly correlation, affects the Hall conductivity and changes the sign of the carriers. And one can ask, what's going on here? Why does this expression give you change of sign of carriers? Well, first of all, this is a calculation based on a model, but it's it has correction terms which are now evaluated but assumed to be small. But this change of sign still survives the correction terms. And it's been confirmed by separate calculations in quantum Monte Carlo by the Devereaux group in Stanford last year. They found, using a slightly different model, the Hubbard model, a similar increase in the Hall conductivity towards half filling, and again, sign is the same as ours. So the only explanation I can say is, let's look at another system that has a Mott transition and see if we see the same effect. And that's a system of bosons on optical lattices, in fact, realized by Manuel Bloch's group. This is a theoretical paper also based on calculations done previously by Netanel and by Huber and Lindner, and which showed that there are Hall sign reversals when you come close to the phases that are called Mott insulator phases of bosons. These are phases where the bosons, because of strong interactions, just want to sit one at a site or two at a site, integer number of bosons at site, have no phase coherence, and therefore they are not superfluid or not metallic at all. There's a gap. And in between those Mott insulator phases, there's superfluid phases which are described by hardcore bosons. It's very similar to these restricted hoppings of the fermions in the TJ model. And again, Hall sign reversals have been seen. So while the bosons might be charged positively, when you come close to the Mott phase, they switch sign. So a similar phenomena happens with bosons as well, driven by strong interactions. And this is a book I read not long ago, which is called The Speed of Dark. It describes an autistic hero who constantly thinks about the problem of what is faster, the speed of light or the speed of dark, because he sees always that light is advancing and dark is running away at the same speed. So I think we have a similar question here. What is moving, particles or holes? So imagine hardcore particles, completely classical in this case, that can hop around, but they cannot hop on top of each other. And now you can see they're hopping to the right. So you say, okay, the particles are carrying a current to the right. However, if you make more particles than holes, and you still have the same dynamics, that the blue curve, the purple circles are hopping to the right, but keep your eyes fixed on the white circles, on the vacancies, and you can see that the vacancies are hopping to the left. So this kind of gives you a picture which may explain, by hand-waving arguments, why when you're coming close to the Mott phase where everything is occupied, it's the minorities that determine what is moving and what is going to be the Hall sign. So it's the lesser density, if you want. So I don't know if this explanation is correct or useful, but it just goes to show that it's a different consideration that one needs to take into account with strong interactions. So what are the take-home messages for those of you who survived the talk? The Hall effect exposes the moving parts of the conductivity, and the sign reversals can occur due to several reasons. lattice potential, parallels. Of course, it's a highly quantum effect of interference that gives rise to this whole motion. And superconducting flux flow via moving vortex charge, again, a consequence of the rigidity of the superconducting phase. And close to a Mott transition, you get a phase flip, a sign flip due to restricted hopping. And I just mentioned that there are 3 formulas of magnetotransport in this paper that allow us to go well beyond the traditional transport theories of Landau and Boltzmann, which have to assume well-defined quasi-particles. And these are the 2 effects that I hoped I explained. So I'll take questions, and thank you very much.
Thank you, Assa. So let's see, we have time for some questions.
Can I ask a question?
Sure.
Yeah, okay. I was interested in the idea, which I didn't know about, called which you call the vortex charges. Can this vortex charge be experimentally measured? And if so, I mean, is the way that it can be done using a scanning tunnel microscope? Can you say a little bit about that?
Yes, I wish that it was carried out. I know that one group, actually Zhao's group, actually Kim's group in Harvard, is trying to do that using SET, the single electron transistor bridges, which are very sensitive to electric fields. The electric field is not large, so the vortex charge will produce a tiny electric field, and most of it will be screened back by the surrounding metals. So to see it, you have to come very close to the superconductor. Yeah. And I know that Misha worked hard on seeing the vortex charge, and so far there's no decisive answers about whether he was able to.
That's why I thought a scanning tunnel microscope might be a suitable instrument for that, because that comes very close to the surface. Right.
In a scanning tunneling microscope, one would look at the IDV and integrate over V to get essentially the charge. So I haven't seen conclusive results from that. People haven't looked for it, I think, well enough. Or maybe they looked at it before the technologies were developed, because this is a very old problem. There's also possibilities of perhaps in a capacitance, measuring a charging of a capacitor plate by applying a magnetic field to a superconductor. And again, there were some preliminary results that weren't published, so I can't really say much more about it, but it's a very, I think, important thing to look for.
Thank you.
Thank you.
Actually, I mean, one question about that. So the electric charge that you see is of order of 1 per vortex. I mean, if from fitting to the experiments.
Yeah, from 0.1 to 1. Yeah.
What do you say? Sorry.
From 0.1 to 1 electron per vortex.
Yeah. I see. But that's also like spread over the entire layer. Mm-hmm.
It's spread over the unit cell of the vortex lattice. It's per layer.
I mean, it's per layer, or it's for the entire film, like, you know, the vortex going through the entire film.
Okay, that's a good question. The films that the Kim group had is very, very thin. I mean, they're like 3 or 4 layers. So, and a lot of that charge is screened within the sample. So if you take a 3-dimensional sample, it's difficult to see that charge, because if it's a large, bulky 3-dimensional sample, most of the screening will be done between the layers in the dopant layers. So you're looking at the last uncompensated layer, let's put it that way, and seeing whether it can send field lines outside of the sample. Okay, that's essentially what is needed to. Or a superconductor that is lying on top of a gate that could be gated, like these twisted bilayer graphene, and there's now thin films, even on conventional superconductors, that allow charging through a gate, and then you can measure it.
Yeah, other questions?
I have a remark. It's also in Corona. that the minorities dictate where we are all going.
Yeah, okay.
I have a question.
Sure, yeah.
So the charge, this charge, vortex charge, is it strong enough to change in substantial way the interactions between vortices such that you will actually be able to see this?
No, it's much, much weaker than the interaction. The interaction between vortices is governed by the stiffness rho. And this is a derivative of the stiffness with respect to density. It's essentially the charge that you attract by trying to minimize the kinetic energy a little bit by changing the superfluid density. You're putting a stress by, whenever there's a twist and a vortex, there's a stress on the system, on the Ginzburg-Landau free energy. And that stress can get released a little bit by attracting charge. So it's a secondary effect to the vortices and to all the physics of the vortex lattice. So I don't think, it significantly changes, the strong logarithmic interactions between vortices.
May I ask a question, please?
Sure.
Hi, Assa. So related to the previous questions about charges of vortices, so the vortex in the vicinity of the vortex is a soliton. It can bind particles like solitons in other theory. So by solving the bound states of the vortex, can you actually account for the experimentally detected charge? And can it also exhibit fractionalization of the charge?
No, okay. We talk about superconductors with large psi and large cores, especially close to TC. The physics inside the core is really just a metallic inclusion of the normal state. What you're talking about is very small vortices, things that are kind of reminiscent of the quantum Hall effect, that you maybe have a single state in the middle of the vortex. Here you have, many millions of states in the vortex, and they're all essentially occupied up to the Fermi level, and the Fermi level changes little between, the inside and the outside of the vortex. So most of the charging is driven by the strong currents around the vortex.
Okay, thank you.
Yeah.
Okay, are there any other questions? Okay, if not, let's thank Assa for this very interesting talk.
Okay, thank you very much, and go and have the cookies that are waiting for you.
You can teleport them, no?
They're in the mail. They're in the mail.
Okay, thanks, Daniel.
Thank you.